So, here we discuss about the convergence of the sequence R raised to n. The sequence R raised to n converges if minus 1 less than or less than or equal to 1 and limit of the sequence R raised to n is equal to 0 if minus 1 less than or less than 1, and when R is equal to 1, the limit is equal to 1. Okay? And the sequence diverges for all other values of R. It diverges for all other values of R. Let us show this. We show this by taking, suppose, case 1. Case 1, when R is equal to 0. When R is equal to 0, then all the sequential terms of the sequence R raised to n is equal to 0. So the sequence will be something like 0, 0, 0, etc. So definitely it converges to what? Converges to 0. Okay? So when R is equal to 0, the sequence converges to 0. So the second case is 2 when 0 less than mod R less than 1, that is minus 1 less than R less than 1. This case, when minus 1 less than R less than 1, since mod R is less than 1, there exists a, since mod R is less than 1, there exists a positive number P such that mod R is equal to 1 divided by 1 plus B, right? When 1 is divided by a quantity that is greater than 1, then that result will be less than 1. Okay. So mod R is equal to 1 divided by 1 plus B. We can find a P such that 1 divided by 1 plus B is equal to mod R. So, now using binomial theorem, binomial theorem, 1 plus P all raised to n is equal to 1 plus NP plus n into n minus 1 divided by 2 into p square plus etc. Right? And this quantity is clearly greater than NP. Right? Since all the terms are positive, 1 is positive, n into n minus 1 divided by 2 into p square is positive. Since p is positive, all the quantities on the RHS of this expression is positive. So this quantity will be clearly greater than NP. Okay, this quantity will be clearly greater than NP. So mod R raised to n. So mod R raised to n. Mod R raised to n is equal to 1 divided by 1 plus p raised to n. Okay, 1 divided by 1 plus p raised to n will be less than 1 divided by NP. Okay? 1 plus p all raised to n is greater than NP. So the reciprocal will be 1 divided by 1 plus p raised to n will be less than 1 divided by NP. Since mod R is positive, so this is 0 less than mod R raised to n less than 1 divided by n. We can rewrite this as that is 0 less than mod R raised to n is less than 1 divided by n. Okay. Now the sequence 0 converges to 0, 0, 0, 0, etc. 0 converges to 0, and since P is positive, and when n tends to infinity, when n tends to infinity, 1 divided by np tends to 0, right? The denominator is increasing, so 1 divided by np tends to 0. 0 tends to 0 and 1 by np tends to 0. So the sequence r raised to n also tends to 0 using sandwich theorem. Okay. So by sandwich theorem, what's Squeeze theorem? So by Squeeze theorem, mode r raised to n converges to 0. Therefore, r raised to n converges to, when mod r raised to n converges to 0, so r raised to n also converges to 0. Right? Now, the third case 3. When r is equal to 1, all the sequential terms are r raised to n. So all the sequential terms are equal to 1. 1 raised to n is equal to 1. So definitely the sequence converges to 1. Okay. Now the fourth case 4. When r is equal to -1. When r is equal to -1, then the sequence r raised to n will be, this is equal to -1, 1, -1, 1, -1, etc. Right? Clearly this is an oscillatory sequence, so the sequence diverges. Hence we prove the result. The sequence r raised to n converges if and only if -1 less than or less than or equal to 1, and the limit of that sequence is equal to 0 if r is in between -1 and +1, and when r is equal to 1, the limit is equal to 1. And in all other cases, all other values of r, the sequence diverges. Okay? Now let us discuss some examples. When an is equal to 1 plus -2 by e the whole raised to. So first problem, n is equal to 1 plus -2 by e all raised to. We know that the value of e is 2.71 something. So this is denominator is clearly greater than the absolute value of the numerator. Right? So modulus of 2 by e is less than 1. 0 less than modulus of 2 by e is less than 1. So this quantity by this theorem, this quantity tends to 0. This tends to 0. So this quantity tends to an tends to 1 plus 0. That is equal to 1. So the limit of this sequence is equal to 1. Is it easy? Now let's discuss another example. an is equal to 2 raised to n divided by 3 raised to n plus 1. Now we can rewrite this as, this is equal to, dividing the numerator and denominator by 3 raised to n, we get 2 by 3 the whole raised to n divided by 3 by 3 the whole raised to n is 1 plus 1 by 3 the whole raised to n. Right? Now 2 by 3, the absolute value of this is less than 1. So 2 by 3 all raised to n converges to 0. Numerator converges to 0. 1 by 3 all raised to n converges to 0. And 1 plus 1 by 3 all raised to n converges to 1. So this quantity converges to 0 divided by 1, and that is equal to 0. Okay? Now another example is an is equal to 2 raised to n plus 1 divided by e raised to n. This can also rewritten as 2 by e the whole raised to n plus 1 by e the whole raised to n. Right? Clearly, this converges to this quantity converges to 0 since E is greater than 2, and here also this converges to 0, so 0 plus 0 is equal to 0. Limit of that quantity is also equal to 0. Okay? Now let us discuss another problem. If limit of a to n is equal to n and limit of a to n plus 1 is equal to n, then limit of a n is equal to n. The even times of the sequence an converges to n and the odd times of the sequence converges to n. So we have to prove that the sequence converges to n. Okay, let us prove this. Suppose epsilon greater than 0 be given. Let epsilon greater than 0 be given. We want to show that there exists a natural number n such that modulus of an minus n is less than epsilon for every n. This is a natural number, capital. Okay. For every n greater than this n. Okay. This is what we need to prove by the definition of the convergence of sequences. Now it is given that limit of a to n is equal to n since limit of a to n is equal to n. By the definition, there exists a natural number capital N1 such that modulus of a to n minus n is less than epsilon for every n greater than n. Similarly, since limit of a to n plus 1 is equal to n, since limit of a to n plus 1 is equal to n, there exists another natural number, say n2, such that modulus of a to n plus 1 minus l is less than epsilon for every n greater than n2. Let n be the maximum of this n1 comma n2. If n is the maximum of this n1 comma n2, then modulus of a to n minus l will be less than epsilon, and modulus of a to n plus 1 minus l is less than epsilon for every n greater than this n. That means all the sequential points lie in the epsilon neighborhood of this n. Therefore, modulus of an is less than epsilon for every n greater than n. Right? The even times of the sequence lies in this epsilon neighborhood of n, and the odd times of the sequence also lies in the epsilon neighborhood of n. That means all the sequential points lie in the epsilon neighborhood of n. Therefore, limit of an is equal to n. This is what we need to prove. Okay.